Let's take a look at some new malware uploaded to Malware Bazaar. So this has been uploaded by Monitor SG, and it has the tag ClearFake. Now, ClearFake is a family of malware that's been around for about a year, and it was first discovered by Randy McCohen. Now, Randy details how this malware actually functions in his blog post. Basically, the end result is that it's going to try to prompt a user with a fake browser update. Now, if they download that fake browser update and run the script, this is going to infect their computer with a different family of malware. ClearFake is a little bit interesting in the way that it does this, so I definitely recommend that you dive into his blog post to understand more about how this malware functioned when it was discovered. But it has since evolved, so I also recommend that you take a look at Sekoia's blog post. The reason being is because this malware has evolved to use the Binance Smart Chain. So what it does is it actually uses a smart contract to deliver part of the JavaScript that's going to be run that then prompts that fake browser update. Now, this is a technique that's been dubbed ether hiding and is a little bit novel. This is actually probably the only family of malware I know that uses this technique. So let's dive in and actually see how it works. So based on the Sekoia blog post here, we know that ClearFake actually uses JavaScript all throughout its chain. If we look at the Malware Bazaar submission, you can see that Monitor SG has mentioned that there is the Binance.org subdomain that's being accessed by some of the malicious JavaScript on a website. It has a particular Binance key, or a particular Binance identifier, I should say, and this is actually for the smart contract that's going to be run. And then it results in a PowerShell script being downloaded that then, once run, is going to pull down a zip and execute it by the looks of things. So the first thing I want to do in my analysis is take a look at this Binance identifier, because this is going to be identifying the smart contract that is being used in this malicious campaign. Now, if we take this identifier and go to BSC scan, which is the Binance Smart Chain scanner created by Etherscan, we can actually punch this in and see the contract. We can also see who created the contract and a bit more details associated with this. So the creator of the contract doesn't actually have any kind of indication that this is controlled by a malicious threat actor, but it is, right? Now, a contract in itself can be viewed online, so we can actually go to this and decompile the bytecode. However, there's a bit of a problem, and the problem is that there's a number of methods that are defined that can be run, and we can see that that's going to be run here, but it doesn't actually give us the details about this contract when it's actually run. Let's actually take a look at how this smart contract works by interacting with it. So we actually get something a bit more useful than just this defined method that's going to be run. So I've just gone ahead and opened up my console in Google Chrome, and I've created a script that's largely based off of the malicious script that's going to be present on websites. And I got this from the Sekoia website. The script is based off of this one here. The difference being, I don't want to evaluate what comes from this smart contract with this eval ATOB and link. So ATOB is going to convert base64 encoded string, just to give you an idea that that is going to be what comes back from this smart contract. So I don't want it to do that. So I've actually tailored it just a little bit. What is actually going to happen is we're going to implement the ethers script because we need that on our page to be able to run properly. Then we're going to define a provider. In this case, the provider is the Binance.org provider. And we also get this smart contract address that we have here. Now, we have a bunch of inputs that I haven't tailored at all because this is exactly what the malicious script is doing in itself. So I didn't want to change that. And then we define the new contract that we get. At this case, I'm just going to log it to my console. Once this script runs, it's going to run the load function that we've defined, and that is an asynchronous function right here. So let's actually just run this script. And we can see, okay, ethers is not defined. So that means there's an issue with the way that I have imported this particular script. Okay, now it does function. I guess in the first instance, we are appending it to the page and it didn't work quick enough, so it didn't actually function. But we do have it here now. And you can see that the response seems to be this base64 encoded string. Now, this is completely different to what we saw in the smart contract decompiled. So let's take this over to CyberChef and let's actually decode it. So we're going to do from base64. So now that we've got it from base64, what I'm going to do is I'm going to take it and I'm going to take it to obfuscated.io because a lot of JavaScript that's being being used by malicious threat actors are just obfuscated using obfuscator.io. This deobfuscate function is going to work quite nicely to get us what we need. You can see it doesn't make a lot of sense looking at it. Maybe we can see the starts of maybe some domains that are being mentioned here, but let's actually just hit deobfuscate and bada bing, bada boom, we have what we need. So this actually has now the next endpoint that this is going to be run against to pull that next stage of our payload. Now we can actually match this up. So there is this ryr.xyz, and if we look here, we can see ryr.xyz. So Monitor SG has actually laid out this attack chain pretty nicely for us. So now we can actually pivot based on some of the other indicators that we had. So this .xyz domain, let's actually take this endpoint and let's take a look in something like URL scan. We're just going to run a search for it. And you can see there's lots of different endpoints that are mentioned. There are actually a few websites that come up. So this alightfromheaven.org, if we actually take a look at this, okay, it says there's no screenshot available, but it does look like it's based on WordPress. So immediately I'm beginning to think, okay, maybe this website's been compromised. If we look at the requests, we can see the same activity that we saw before, where it does use this binance.org, the smart contract, and then it's going to use that smart contract to eventually reach out to this domain. But one of the other things that we haven't pivoted based off of is that actual Binance smart chain domain that's being reached out to, because we know it's being used in this malicious campaign. And how often would this actually be sitting as a smart contract to run on a website? I'm going to go ahead and say barely ever, if never at all. So let's actually take this data seed, this BSC data seed, binance.org, and actually run a search for just that domain in URL scan. Oh dear. Search results 100 out of 8,253. That's not great. It does look like there's quite a lot of websites that have been compromised that is hosting this particular fake browser update. Now we could actually go on to some of these and see if the behavior looks the same. I'm just going to spot pick some randomly. And if we take a look, we've got a website, looks like a legitimate website. It is based on WordPress. Let's take a look at the requests, and we can see this ethers script, something that would also be good to pivot off of, because without that, you're not able to get the smart contract. And then we see the endpoints and the responses associated with those endpoints as well. And if we actually look, this looks like it's a base64 encoded string. So this looks like the response from that smart contract in question there. So let's actually just take that one. Browser work correctly. This looks like it might be a test. It doesn't look like it's actually responding at this point in time with a base64 encoded string that then when it decodes is going to give the malware in question. But if they were able to infect a website and then have it run this smart contract, they can change what the smart contract does. So taking a look at these endpoints when they come back is going to be a good idea. We've got another Binance one here. We have the binance.org, and then we have an endpoint. This is a different endpoint. Let's take a look at the response from that. We have a different base64 encoded string. So let's actually take this base64 encoded string. I'm going to copy all of that. We're going to put this in here. We begin to see a few other things of interest. So this looks like it's actually a base64 HTML content that's specified, and it's creating something in the page in question. So let's actually take that and decode that base64 and see what might be displayed. So it does look like there is a HTML page that's specified here. It does look like there's pop-ups mentioned. Let's go down. Oh dear. Something went wrong while displaying this web page. There was an error during the latest update of your browser version. Here's what you need to do to update your browser, which includes running a Windows PowerShell script as admin. So immediately we can begin to see how this attack chain pans out. It makes that connection to the smart contract, and the smart contract then presents a pop-up that goes above the web page they're trying to access to say their browser is out of date and they need to update. And then as a result of that, they download this PowerShell script, they're going to run it as administrator, and then it's going to deploy malware on their system. And just to show you a little bit more, there are actually translations here. So this is only the English pop-up. So if you were to be in Russia, it would then present it with Russian text. Yes, it's going to get, I believe, Spanish, and so on and so forth. There's support for all different languages to say that your browser is out of date, and you should be running this malware script as administrator. So I've gone ahead and downloaded the HTML, and this would pop up over their website, and the user would be sitting there going, oh, okay, there's an error, and it's got clear instructions. What's interesting is if you click on that, it's going to copy text to your clipboard. So you can see it's copied the entire PowerShell payload that's going to be run to your clipboard if you click copy fix. So then you're going to do that. Then you have to right click the Windows terminal and hit the Windows PowerShell as admin, and then you're going to run that script by pasting it in there. And this is something that a user might easily be able to do and not understand what they're doing. It's a little bit interesting the way that this script works. If we take a look at it, you can see that down the bottom, there is this text to copy, and it has a listener for when you click that button, so it can copy text to your clipboard, and the entire payload that's going to be run is actually embedded within this JavaScript that gets deployed here as well. Unless there's an issue, in which case it just says unable to copy text to clipboard, but this is in the console on your browser. And if we take a look at the payload that was copied to the clipboard in this instance, we do see that it is using from base64 encoded string again. So looking in CyberChef, we can see that this one is actually reaching out to this other website. Maybe it is another compromised website, and it's getting the content from this cow.html. So you are then going to be downloading that data from that cow.html and specifying that in the argument list and executing it. So let's actually take a look at this cow.html just to see what this would be deploying on an endpoint. So taking a look at this, it does look like it is a compromised website. It is based on WordPress, not surprising. We can actually see the payload that's going to be returned here. It does look like there's another zip file on the compromised website itself. So if we take a look at the response, there is going to be this get random sleeping, and then it's going to go out and download this zip. It's going to be downloaded to a file called helper.zip. It's going to be extracted, and then it's going to have the executable within it run. And so we can confirm that that website was actually compromised and hosting the malicious payload. So let's actually dive into the PowerShell script to see how this functions on an endpoint and what malware it might be delivering. So I've gone ahead and downloaded the PowerShell script, and the first thing I can see is that it's going to be using WMI, so the Windows Management Instrumentation Framework, to actually get information about the thermal details on your system. So the temperature, it's probably got a good idea that if it's running in a sandbox, it's not going to have thermal information that shows a temperature over a certain amount. But if it is a legitimate system that's running, maybe it does. We can see environment.exit. So this is anti-sandboxing technique being used here. We can see that it sets the clipboard to nothing. So if you've got anything copied to your clipboard, I guess it just gets rid of that value. It then adds a Windows Defender exclusion in your app data directory and the program data directory. So we can see that it does create an exclusion, and it does also check to see the exclusion has been added properly. Then we see that it sleeps for a second, and then what it's going to do is it's going to be getting date. I don't know why it's doing that. I guess date and time is going to be used somewhere in this script. We can actually take this variable and see whether it's been used, and it is. It's used this in this one section. It's being defined in this variable here, and if we take that variable is going to be copied into this one, and then this one's going to be used here in script block AST. So we can see that the get date function is used as well. But the main thing we're interested in seems to be this giant base64 encoded data. So let's actually take this and do some analysis on it, because this is what's going to be deployed on an endpoint or running on an endpoint when this PowerShell script is run. We can tell that by this invoke method down here. So let's head over to CyberChef. All right, I've just put in the base64 encoded data. However, what we don't want is these null bytes. So let's remove these null bytes. And now we actually get the next stage of our payload. It does look like it's using some sort of encryption because there is mention of AES, this padding mode, which is PKCS7, the cipher mode, which is CBC. The good thing is it is kind of giving us everything we need to decrypt this, unless there's something to do with the key. It does look like it's using bytes for the key that's being defined in K. So we have to figure out what K is. And K looks like it might actually be something passed to this. Let's take this step by step and actually do some analysis. So the first thing I'm going to do is try to neaten up this script. I might even just be able to do a generic beautify. And we can see straight away this is actually giving us something a little bit neater. So now we can begin to do some analysis. Let's take this, put it back into a new section in Notepad++ and do some analysis. So let's take this script one step at a time. One of the first things I want to do is take these base base64 encoded strings and make them something a little more legible. I've taken the first one and we have an output value here. So this output value is going to be that. And we're going to take the next one. And we have this value here. So now we seem to have K and V defined, and so that might be a key and maybe an initialization vector. E is likely to be the encrypted bytes. So if we take this and base64 decode it, we're probably not going to get anything legible. And we don't. It's gibberish. That's okay. Let's do some analysis here now. We can actually see most of it is done within function B. So there seems to be a bunch of defining for the encryption. We can actually see that there is a define initialization vector, which does seem to be using the value V. We can also see that there is a key, which does seem to be using the bytes defined in K. So this is something that now gets us on our way. We do have the key size and the block size and the other details associated with how encryption is playing out in this case. So without going too much into the detail, this kind of just looks like it's being used to convert hexadecimal values because it does have this byte and this 16. So this is likely just being used to get kind of byte representation. We do have a formula that's being used down here and invoke expression being used on the output of that. We kind of can see what this is doing. They haven't made this very difficult at all. If we take this base64 encoded string, which is also encrypted, and we punch this in here, what we're going to do is we're going to do from base64. And now that gives us the jumbled output in its raw format. Now what we're going to do is actually just look at K and V and how this is performing encryption within this function B. We have the values that we decoded. So let's do an AES decrypt. Now the key, we do have a value here. This isn't in hexadecimal. This is actually UTF-8 because we've converted it from that base64 encoded string and it's actually encoded in UTF-8. So let's take UTF-8 there. Now the IV we worked out here. Now this has only got numbers and letters and it only goes up to the letter F. So we can immediately see that this is actually using some sort of hexadecimal. So we're going to keep the encoding here as hex. Now we have the mode as CBC and we do have the mode as CBC. The actual iterations of 128 should automatically be determined based on the key and the initialization vector that we've given it. So we don't actually need to do that, but the input is raw because remember, this was encrypted and we went from base64, so we had it in its raw format. So let's actually change the input to raw. And now it looks like we have the next stage of the PowerShell script that's going to be run without too much trouble at all. Let's actually just take this and do some analysis on this. So this looks like it's getting a random value. It's going to sleep for however long of that defined random value. Then it's going to define your TLS or your SSL3, everything to do with a secure network connection to actually be grabbing the next stage payload. And it does seem that it's going out and reaching this from this exec resource.ltd. So this is that next stage, which is what we saw in the Malware Bazaar submission. So it goes out and it gets a enc.zip and it deploys it to a temporary path. Then from there, it looks like it writes all of the bytes associated with that. So the file is downloaded properly. It creates a directory for it. It then extracts that zip file to that directory, and then it looks for any executable files in that directory, gets the first executable that it finds, and then it's going to use the system diagnostics to actually execute it. And it's going to execute it with a window style of hidden and start it. So now we actually know where we're focusing the next part of our effort. So let's jump in. So I've gone ahead and extracted that archive, and this is what it looks like. We know that it is launching the executable in this directory, so this impacker.exe. So let's actually take a look at whether that has any antivirus results on VirusTotal. So I've uploaded it and it says, oh, it's a potentially unwanted program. And it is signed. It seems to be an MFC application. This might lead people to think maybe this is just adware, but they'd be wrong. And it's not a PUP either. I mean, technically this executable is, but it's not the executable we're actually interested in. What I'm going to do is take every single one of these DLL files that are in that directory and upload them to VirusTotal. So we've got the first one. We're going to do some analysis. Oh, and we can see, yep, okay, potentially unwanted program. It is signed. All right, let's take the next one. Compare that hash, potentially unwanted program. It is signed. This one's more interesting because it didn't verify So it actually says that it did not verify. There is also a mention here of one of the names was payload_1 when it was submitted. So we might actually have a case where this DLL has been modified and is actually being used to run some malware. Let's keep going through. So we have the next one. This one's signed and it's valid. We have this one. It's signed and it's valid. This one is signed and valid. This one is signed and valid. This one is a known distributor. It's not signed, but it is classed as a known distributor. So we can look away from that one as well. Valid, known distributor, known distributor, known distributor. And this one is also, once again, signed and valid. And this one's signed and valid. So why is it that they're all signed and valid besides this one? This incredilook ex.dll. And what's up with the other files that are in this directory? There seems to be an SQL file, but if we use detected easy, we can see it's just flagged as binary, which is not something we would expect to see with an SQL file. We also have a zip file. Surely if we look at this with detected easy, also says it's binary. So these look like they have some sort of mismatched extensions. They're not actually the file types that they are perpetrating to be. So looking at the fact that we have one of the DLLs that seems to have been modified to break the signed certificate associated with it, and the mismatched extensions here where there's a zip file that isn't actually an archive and there's an SQL file that isn't actually a SQL database. What we actually likely are looking at is IDAT or hijack loader. Now I know this from previous analysis that I've done in another video, which I will link in the description below, but let's actually take a look and see if we can confirm this in any way, shape or form. Now I have actually created a rule to detect IDAT or hijack loader. Now this is based off of the research from Rapid7 Labs. It's not a complicated rule at all. It's actually just looking at the constants within the payloads that are being used and deployed within IDAT or hijack loader instances. What it's doing is actually looking for that known offset, which is going to be defining the encryption key, and that's going to allow me to understand that this is likely IDAT or hijack loader. There's also a configuration extractor that Rapid7 Labs created, which we will be using if we get a hit on this to understand the final payload that's going to be deployed into memory from this ClearFake campaign. So let's actually go ahead and do some analysis. So I'm going to go ahead and open up a command prompt here. And what I'm going to do is run a Yara rule against the ClearFake directory where we've got all of those payloads to see if there's any hits. So I'm going to run Yara 64. I'm going to give it the rule that I've created here, the shellcode loader rule. Then I'm going to specify that it needs to be recursive and specify it against the ClearFake directory. And you can see straight away we have a hit on this torpor.zip for the IDAT loader encrypted payload. That's actually what we're going to use the Rapid7 decryptor against to try to see if we can find out what the final payload being delivered into memory is. So I've got the Rapid7 extractor here, and it is a Python script. So I'm going to run this. I'm going to run Python. We're going to run it against the IDAT extractor, and I believe we can just specify that and a input file, which is going to be used against. So let's go back to our defined file here that we found. And we can see it's found the XOR key, the config size, and it's wrote the final payload to a location on our endpoint. So that's great. Let's take a look at this bin file to determine what is actually being deployed into memory at the end of this ClearFake campaign. So we do have the final payload here, and I'm just going to open this up in PE Studio. So while it performs this analysis, I might hit it with a floss as well, just to see if there's any kind of output from that allows us to get more idea on what this malware is. Looking in PE Studio now, we can see a number of strings that have been found, including this FTP and CMD, seemingly looking strings in the binary. In these sections, we can actually see that there is a section with this JACTL, which is unusual and a little bit interesting. So something that we could probably pivot off of to see if there's anything else that uses that section name as well. And so straight away from our strings output, we do see once again this Luma no work, which we've seen in a previous video, which is associated with the Luma C2 stealer. We actually have a good indication that this is actually Luma C2, and we can see other evidence of that as well within the binary. For example, there is a license key number that is defined in the Luma stealer, which if we look at the strings, we can see the naming convention associated with that. We do see that it's stealing the cookies from the SQLite database and all of that good stuff from browsers. But then there is also this kind of naming convention that goes with a name, a hyphen, and then a identifier like this. And that's a good indication that this is Luma C2 as well. When combined with that, there is also mention of name equals ATOC, which is one of the known indicators of Luma C2 as well. So now based on our analysis, we know that ClearFake is compromising websites, then is using the Binance Smart Chain technology to deploy fake browser update to endpoints that then, if someone uses the fake browser update instructions by downloading the script and running it as administrator, it's going to deploy Luma C2 Stealer on the endpoint that's going to steal their credentials, their session tokens, and all that other information that's going to then be used however it wants to be used. Maybe it's being sold to threat actors, or maybe it's being used to compromise your environment. So that's it. That's all I wanted to show you today. Thanks so much for sticking in. Let me know your thoughts, feelings, comments, anything else in the comment section below. Don't forget to give a like and subscribe if you enjoyed this video, because it didn't cost you anything and it cost me time. Thanks so much, and I will catch you next time.